Welcome back to the deep dive. Today, we're tackling something really fundamental.
Foundational is the right word.
Yeah, the decimal number system. We've got some fascinating research here proposing, well, a pretty revolutionary way to look at it.
It aims to unify how we teach and really how we think about numbers.
Exactly. To strip away all those, fragmented rules we all learned,
The ones that treat whole numbers and decimals like completely separate things.
which, as the research points out, causes so much confusion. Think about it. How many of us, even now, kind of rely on these little tricks?
Oh, absolutely. Procedures learned by rote, not really understood,
Yeah.
especially when you cross that decimal point boundary.
And the classic example they give, the one we probably all heard,
Let me guess. Just line up the decimal points.
that's the one. And the material argues that's just a symptom, right? A procedural fix that doesn't get to the heart of it.
Exactly. It avoids the why. Why do they need to line up? It's not about the punctuation mark itself.
It's about the values, the places.
Right. You're lining up digits that share the same place name, tens with tens, tenths with tenths. And avoiding that core truth, well, the research suggests that's a barrier to real number sense.
Okay, so the proposed solution we're diving into today is this thing called the new place value chart.
It's designed specifically to force that unification, to push past the tricks.
And get us thinking, well, algebraically about numbers.
That's the key. The core idea, the real innovation, is making a very clear distinction between a digit's position, its place name, like hundreds or tenths, and the actual mathematical value of that position.
Position versus value.
That separation, that dual approach, is what creates the consistency. It works for all numbers, big, small, whole, decimal. It's one system.
So that's our mission for this deep dive. We want you, the listener, to really get your head around that core innovation.
How moving from just rules to understanding the structure makes everything click together. Addition, subtraction, comparing numbers.
Even trickier stuff like rounding, apparently.
It all becomes much more consistent.
Okay, let's get into it. Let's unpack this algebraic foundation they're talking about.
Okay, so right at the heart of this unified model is something the research calls the golden rule of place value.
The golden rule. Sounds important.
It is. It's foundational because it explicitly defines that relationship we just mentioned, the link between the digit you see and where it's sitting in the number.
And how does it state that rule?
It's actually beautifully simple. To find the true value of any digit, you must multiply the digit by the value of its place.
Multiply the digit by the value of its place. Okay, so location turns into a calculation.
Precisely. Think about the number 35. We see the digit 3.
Yeah.
But its true value isn't just 3. It's sitting in the tens place. And the tens place itself has a value of, well, 10.
Right.
So the Goldie rule says the true value of that 3 is the product. 3 times 10.
Which is 30.
Which is 30. That's the definition, really, boiled down to a basic algebraic step. We often just skip over that explicit multiplication in our heads.
We just know it's 30, but we don't think about the times 10.
We don't articulate the why. And this is where movement on the chart becomes critical. Let's take that same digit, 3, and slide it one column left, say in the number 305.
Okay, so now it's in the hundreds place.
Exactly. The position changes. The value of that new place, the hundreds place, is 100.
Right.
So applying the golden rule again, the true value of that 3 is now 3 times 100.
300, a much bigger value.
Dramatically bigger. And it's the single multiplicative idea, digit times place value, that underpins everything. We often miss this when we just memorize column names like ones, tens, hundreds.
We see the names.
Yeah.
Not the underlying values or the multiplication.
And what the chart does is formalize what the research calls the movement rule. This isn't just a coincidence. It's presented as a fundamental law of our base 10 system.
The movement rule.
Okay.
This sounds like the key to the unification part.
It really is, because it applies equally whether you're dealing with big whole numbers or tiny decimal fractions.
So what does the rule actually state?
2 simple symmetrical principles. First, every time you move a digit one step to the left on the chart, its place value gets multiplied by 10.
Okay, left is multiplied by 10, like going from ones to tens or tens to hundreds.
Exactly. The place values go 1, then 1 times 10 is 10, then 10 times 10 is 100. It's an exponential increase.
Makes sense. And the other way,
Conversely, every time you move one step to the right, you divide the place value by 10.
divide by 10. So hundreds divided by 10 gives tens. Tens divided by 10 gives.
Ones. The value of the ones place is 1.
Okay, that works for whole numbers.
Uh-huh.
But the claim is this unifies things. How does it work with decimals?
That's the beauty of it. The rule doesn't change. Start at the ones place again, value 1, move one step right.
Okay, so we divide by 10.
We divide by 10, and 1 divided by 10 is
1/10 or 1/10.
exactly. That's the value of the tenths place. Now, move one more step right from tenths.
Divide by 10 again. So 110 divided by 10, that's 1100.
100th, the value of the hundredths place. The relationship multiply by 10 going left, divide by 10 going right, holds perfectly across the whole chart.
Ah, I see. So the fact that the same mathematical operation, the same factor of 10, governs movement on both sides of the ones place. That's the link.
That's the fundamental connection. You're always multiplying or dividing the value of the place by 10. It doesn't matter if that value is 1,000 or 10 or 1 or 1,000th. The algebraic principle stays the same.
Okay. That consistent structure then lets us do something interesting with decomposition, right? More than just breaking a number down.
Yes, decomposition becomes less of a classroom exercise and more like an algebraic proof of the number's internal structure. It shows you mathematically what the number is.
Let's use their example, 2453. How does this approach decompose it?
Well, the key is using multiplication and addition, reflecting that golden rule. We don't just see 2, 4, 5, 3. We see 2 times the value of its place.
Which is the thousands place, value of the 1,000. So 2 times the 1,000.
Plus 4 times the value of its place.
Hundreds place, value 100. So 4 times 100.
Plus 5 times its place value.
Tens, 5 times 10.
Plus finally, 3 times its place value.
Ones, 3 times 1.
So the full multiplicative decomposition is 2 by 1,000, plus 4 by 100, plus 5 by 10, plus 3 by 1. That reveals the mathematical identity.
You know, that's really different from how I think most of us visualize decomposition. We usually jump straight to the result of those multiplications, right?
We do. We tend to see the addition-only version, 2,000 plus 400 plus 50 plus 3.
Which is arithmetically correct, of course.
Of course, it adds up to 2453.3.
Yeah.
But it's the result. It's the arithmetic view, the multiplication addition version, the 2 by 1,000 plus 4 by 100. That's the algebraic truth. It shows the structure before the calculation.
It shows the digits 2, 4, 5, 3 acting like coefficients multiplying these powers of 10.
Exactly. It shows they're just coefficients multiplying the place values of 1,110, 1. The structure makes it clear that the number is simply the sum of the true values of each digit. It's like a polynomial expansion, but using base 10 values.
Okay. So being able to do that multiplicative decomposition easily, maybe using the chart as a guide, that's like a test of whether you really get the structure.
I think so. It forces you to acknowledge the underlying math, the digit times place value idea, rather than just looking at the numbers face value.
Okay, so we've got this golden rule, digit times place value, and this movement rule, multiply or divide by 10.
Oh.
A solid algebraic base. How does this change the game for, everyday arithmetic, like adding and subtracting?
This is where we really see the benefit of moving away from procedural tricks.
Like the infamous lining up the decimal points. We have to ditch that now.
We replace it. We replace that shortcut with a rule that's, well, conceptually honest. It's based on that algebraic thinking. Remember in algebra, you combine, terms.
Sure, you add the x's together, the y's together. You can't just mush 2x and 3y into 5y or something.
Yeah, exactly. You combine things that are the same kind of thing. This model applies that exact same logic to numbers. Digits represent quantities of a specific place value, so you can only directly combine digits that share the same place value.
Meaning they share the same place name.
Precisely. That's the new universal rule for addition and subtraction. When you're adding or subtracting numbers, any numbers, whole or decimal, you always align the digits that have the same place name.
Thousands line up with thousands, hundreds with hundreds.
Tens with tens, ones with ones, and crucially, tenths line up with tenths, hundreds with hundreds, thousands with thousands.
Okay, so the alignment is driven by the column name, the place value itself. What about the decimal point then? Where does it fit?
We'll get into the decimal point more later, but in this context, it's just a marker. It shows the boundary between whole number places and fractional places. The real alignment, the meaningful alignment for calculation, has to be based on the place names.
We push back slightly on the practicality, just for a second. If I've got, say, 12.345 and I need to add 6.7, isn't it just visually faster to spot the two dots and line them up? Why is insisting on aligning place names truly better?
It's better because it reinforces the meaning. Lining up the dots works, yes, but why does it work? It works because doing so automatically aligns the ones with the ones, the tenths with the tenths, and so on.
Ah, okay. The dot alignment is a consequence of the place name alignment.
Exactly. But teaching just the dot alignment lets the student skip the understanding. Aligning by place name forces you to recognize I need to add these 3/10 from 12.345 to these 7/10 from 6.7. It makes the combining like terms idea explicit for numbers.
So you're consciously thinking about adding amounts of the same kind of value, whether it's tens or tenths.
Yes. It moves the focus from the punctuation mark to the actual magnitude of the digits being combined, and that single procedure aligned by place name works seamlessly whether you have whole numbers, decimals, or a mix. Adding 5/10 and 3/10 is the same kind of operation, conceptually, as adding 5/10 and 3/10.
One consistent principle. Okay, that makes sense. Does this consistency also help with comparing numbers? That's another area where decimals get tricky.
Oh, absolutely. Comparison becomes much more straightforward and less prone to visual tricks.
Yeah, like comparing 0.9 and 0.15. That's a classic.
It is. The number 0.15 looks bigger because it has more digits after the decimal point. So kids and even adults might intuitively think it's larger.
And the traditional fix is often what? Adding a zero? Make 0.9 into 0.0 so they look the same length?
Right, another procedural band-aid. Adding trailing zeros works, but again, it doesn't necessarily teach why 0.9 is greater than 0.15.
So what's the Unify Systems approach?
It relies entirely on the place value structure again. The rule for comparison is simple and direct. Start at the leftmost place value column where either number has a digit and compare the digits in that column.
Leftmost digit comparison.
Yes. Whichever number has the digit with the greater value in that first differing column is the greater number. Full stop.
So for 0.9 versus 0.15, the leftmost place with digits is the tenths place.
Right. In 0.9, the digit is 9. In 0.15, the digit in the tenths place is 1.
And 9 is greater than 1.
So 0.9 is greater than 0.15. You don't even need to look at the 5 in the hundredths place. The comparison is decided at the first point of difference, moving left to right.
That seems much cleaner. It avoids the visual length trap.
It anchors the comparison in actual magnitude, starting with the largest place values involved. No need for adding zeros or other tricks.
Okay, to really cement this unification, let's quickly map out that decimal side of the chart again, using the movement rule. We start at ones, value 1.
Move one step right, divide by 10. We get the tenths place, value 110 or 0.1.
Move right again, divide by 10.
We get the hundredths place, value 1100 or 0.01.
Right again.
Thousandths place, value 11,000 or 0.001. And so on. It just continues perfectly symmetrical with the whole number side.
Let's take their decimal example, 24.09. Can we decompose that using the same multiplicative structure we used for 2453?
Absolutely. It follows the exact same logic. The 2 is in the tens place.
So 2 times 10.
The 4 is in the ones place.
4 times 1.
The 0 is in the tenths place.
So 0 times 5 of them.
And 9 is in the hundredths place.
9 times 1100.
So the full decomposition is 2 by 10 plus 4 by 1 plus 0 by 110 plus 9 by 1100.
And notice how the 0 is explicitly included there. 0 times 110. Algebraically, that 0 matters.
It does. It shows there are 0 units of that specific place value. And if we write out the addition-only version, the arithmetic sum,
It would be 20 plus 4 plus 0.0 plus 0.09.
right. And the key insight is seeing that 0.09 isn't just a notation. It represents 9 units of 100th value, 9 times 1100.
That connection back to the fraction, 9 times 1100, seems really important.
It's critical. It solidifies the idea that decimals aren't some weird new type of number. They're just fractional parts, represented using the same base 10 structure we use for whole numbers. It's all powers of 10, just extending into negative exponents, 10 to the minus 1, 10 to the max 2, etc. The system doesn't break, it just extends.
Okay, this next part, based on the material, feels like where this unified structure really unlocks a deeper level of understanding. It's about finding the total number of a certain place value within a number.
Yes, this is what the authors present as a truly crucial skill, one that builds genuine number sense. It moves beyond just finding the value of a single digit, like the 4min in 2453 meaning 400.
Right. That's the golden rule application. This is different.
It's asking a bigger question. How many hundreds are there in total within the entire number 24.09? Or how many tens? Or, and this is the kicker, how many tenths are in a number like 24.09?
That feels more abstract. How do you even find that?
It sounds abstract, but the unified chart, according to the research, makes the answer almost visual, structural. There's a general rule.
Okay, what's the rule?
To find the total number of a specific place value, like hundreds or tens or tenths, within a larger number, you basically ignore all the digits sitting in places whose values are less than the target place value you're interested in.
Ignore the smaller places. Okay, let's try that slowly with whole numbers first. Let's stick with hundreds. If we want the total hundreds in a number, we need to ignore places smaller than hundreds.
Which are?
The tens place and the ones place. Their values, 10 and 1, are less than 100.
Perfect. So let's take an easy number, 300. How many hundreds are in 300?
Well, obviously 3.
Right. And applying the rule, ignore the tens digit and the ones digit, 0. What's left?
Just the digit 3.
Just 3. So 300s now. What about 3,000?
Okay, rule says ignore tens and ones. The digits there are both 0.
What digits are left in the places equal to or larger than hundreds?
We have a 3 in the thousands place and a 0 in the hundreds place.
Read those digits together as a number.
30. 30.
So there are 30 hundreds in 3,000.
Whoa. Okay. The rule just gives you the answer 30.
It structurally reveals the result of the division. 3,000 divided by 100 equals 30. The chart shows you that quotient directly.
That is a shift from arithmetic calculation to just reading the structure. Okay,
Yeah.
let's try the more complex example.
Yeah.
24,053. We want total hundreds.
Apply the rule. What do we ignore?
Tens place, digit 5, and ones place, digit 3. Because 10 and 1 are less than 100.
What digits remain in the hundreds place or larger?
We have a 2 in the thousands and a 4 in the hundreds.
Read those together.
24.
24. So 2,453 contains a total of 24 hundreds.
Okay. That feels weirdly simple. And the research uses another example right after, 2479, to make a point, right?
Yes. Apply the rule to 2479. Find the total hundreds.
Ignore the tens, 7 and 1's 9. We're left with a 2 in thousands, 4 in hundreds. Read
Yep.
together. It's still 24.
Exactly. It's still 24 hundreds. This confirms the rule. The digits in those smaller places, the 53 or the 79, represent the remainder. They don't affect the total count of the larger place value hundreds you're focusing on.
That remainder is just 50, 3100 or 70, 9100 of the next 100.
Precisely. And this skill, seeing the 2400s instantly, is presented as essential for understanding rounding. Instead of just chanting 5 or more, round up, the student first sees the number is 2400s and a bit more. Then they can reason about whether that bit more is enough to round up to 2500s.
It grounds rounding in magnitude. Okay, I'm ready. Let's do the decimal example. This is supposed to be the big payoff, where the unification really proves its worth.
This is the aha moment, yeah. We use the exact same rule we just used for hundreds, but now we apply it to tenths.
The question is, how many tenths are in the number 24.09?
Okay, deep breath. Apply the rule. We're looking for the total number of tenths. The value of the tenths place is 110 or 0.1, so we need to ignore all digits in places whose values are less than 110.
Less than tenths. Okay, in 24.09, the places are tens, ones, tenths, hundreds. The only place smaller than tenths is
The hundredths place.
where the digit 9 is sitting. Its value is 1100, which is definitely less than 110.
So the rule says, ignore that digit 9.
Just ignore the 9. Okay. What digits are left in places equal to or greater than tenths?
We have the 2 in the tens place, the 4 in the ones place, and the 0 in the tenths place.
So 4A2.
Now, read those digits together, considering them as representing the total count of tenths.
240. 240.
240 tenths, that's the answer the source material gives, stating it's taken directly from the chart.
Wow. Okay. Hold on. So 24.09 contains 240 tenths.
It contains 240 full tenths plus that leftover bit, the 900ths, which is 0.9 of another tenth, but we ignore that for the total count of full tenths.
Traditionally, I'd have to think, okay, 24 is 240 tenths, and then there's 0.09, or maybe divide 24.09 by 0.1 calculator, 240.9. Okay, so 240 full tenths, that's calculation.
Right, that's calculation followed by interpretation or truncation. This method, using the chart structure and the rule, reveals the 240 visually, structurally. You just read off the digits down to the target place value.
That is quite elegant. It makes the number 240 kind of pop out from 24.09 when you're looking for tenths.
It's presented as a shift in perspective, seeing the magnitude relative to the chosen unit. Tenths, in this case.
And the research claims this skill, easily seeing the 240 tenths in 24.09, or maybe the 249 hundredths if you went further. That's the key insight needed for properly understanding rounding or truncating decimals.
That's the claim. It removes the procedural mystery. If you need to round 24.09 to the nearest tenth, you first see it's 240 tenths and 9 hundredths. Then you can reason, is 9 hundredths closer to 0 extra tenths or 1 extra tenth? It makes the decision meaningful.
It demonstrates the system is genuinely unified. The same mental operation finds 24 hundredths in 2453 and 240 tenths in 24.09.
That's the core argument. It's not just a different diagram. It's a different way of seeing numerical magnitude driven by a single consistent structural rule.
So moving from the mechanics of the system to how it impacts teaching, the research specifically calls out some common pitfalls, some errors in how we traditionally explain things that this model helps correct.
Yes, it's very practical in that sense. One of the first points is about how we treat the decimal point itself in teaching diagrams or charts.
Giving it its own column or something like that?
Exactly. Or drawing it really large, right next to the ones column, without clearly defining its role. The material argues this can inadvertently give it too much importance, almost treating it like another place value column.
Which would mess up the movement rule, right? It would look like there's this weird barrier interrupting the nice multiply by 10, divide by 10 pattern.
Precisely. It breaks that smooth exponential flow in the learner's mind. The true function of the decimal point is actually much simpler.
What is its only job, according to this model?
It's purely a separator. Its job is to indicate where the whole number part ends and the fractional part begins, where the digits start representing values less than 1. That's it.
So it's like punctuation in the sentence. Necessary when you write the number out linearly.
Absolutely necessary then. But within the structure of this place value chart, the boundary between the ones column, value 1, and the tenths column, value 110, is already clearly defined by the columns themselves. The chart provides the structure. The point is just notation for when the chart isn't there.
Okay, shifting focus away from the point itself. This leads to a specific teaching recommendation, doesn't it? About how we should read decimals.
Yes, a very strong recommendation. Always encourage students to read decimals as multiplications.
Read them as multiplications. How does that work? Let's use 0.09 again.
Instead of just saying 0.09 or even 900ths, the emphasis should be on reading it as 9 times 100th.
Connecting it directly back to the gold rule.
Yeah.
Digit times place value. 9 times 1100.
Exactly. Reading it that way constantly reinforces that decimals represent fractions. They are a quantity, the digit 9, of a specific unit size, the place value 1100.
And why is that constant reinforcement so important? The research links it to preventing a very specific error.
A very common and stubborn error involving fraction multiplication.
Right. The one where students multiply a whole number by both the top and bottom of a fraction.
That's the one. If a student sees, say, 2 times 3/4, 2 by 34.
They might incorrectly write 6/8, 68.
Instead of the correct answer, 6/4, 64. They mistakenly think the 2 multiplies the unit size, the denominator 4, as well as the number of units, the numerator 3.
Because maybe they're thinking of scaling, like making an equivalent fraction.
Possibly, or just confusion about what the multiplication applies to. But the correct understanding is that you have 3/4 and you're doubling that amount, so you end up with 6/4. The size of the unit quarters doesn't change.
Okay, so how does reading 900ths as 9 times 1100 help prevent the 68 mistake?
Because it constantly drills the structure, coefficient times unit value. When you see 0.09 and think 9 times 1100, you are implicitly separating the quantity 9 from the unit size.
1100.
You're seeing the 9 as the multiplier of the unit. Yes. So when you encounter 2x34, that prior training makes it more intuitive to see the 2s as multiplying the quantity 3, not the unit size 4. You're taking 2 groups of 3/4.
The structure used for reading decimals builds an understanding that carries over to fraction operations.
That's the idea. By making the multiplicative nature of place value explicit, especially for decimals, the system builds a kind of cognitive immunity to that specific fraction error. It connects decimals firmly back to their fractional meaning.
It really does seem like this unified chart isn't just a visual tool then. It's promoting a whole different, more integrated way of thinking about numbers.
It aims to replace isolated rules and procedures with a consistent underlying algebraic structure. That consistency, the research argues, is what leads to deeper understanding and fewer errors.
It suggests the difficulties aren't inherent in decimals themselves, but maybe in the fragmented way we've traditionally broken them down and taught them.
That seems to be the core pedagogical argument. Yes. #tag outro.
You know, reflecting on this whole deep dive, the thing that really stands out is that word, consistency.
It feels like the central theme.
We started by talking about the confusion from having, like, separate rule books for whole numbers and decimals. And this approach just tears that down.
It replaces it with one system, governed by that golden rule digit times place value and the movement rule multiply or divide by 10. That's it.
And applying those consistently means we swap out tricks, like line up the dots, for a single meaningful principle, aligned by place name.
Which immediately connects arithmetic to algebraic thinking, combining like terms. It works for 1 milsim or 0.000001. The logic is the same.
So if you're listening, the key things to take away from this exploration seem to be these. First, that idea of the golden rule. The true value of a digit comes from multiplying it by its place value. See digits as coefficients.
Second, when you add or subtract, always align by place name. Think. Combining like terms, whether they're hundreds or hundredths.
And third, maybe the most mind-bending one, is that skill of finding the total place values.
Yeah, being able to look at 24.09 and instantly see the 240 tenths hidden inside. That structural insight is presented as the key to really mastering things like estimation, rounding, truncation. It's about seeing the magnitude.
Right. And that leads us to our final thought, something provocative to leave you with. The research really hammers home that this unified view builds the foundation for rounding and truncating.
It makes it almost intuitive, based on structure.
So the question is, if simply rethinking how we visualize place value can make something like finding the total tenths in a number instantly obvious, bypassing calculation, what does that imply about how we teach numerical estimation and precision worldwide?
Yeah, if the structure itself reveals the answer needed for rounding, does that mean a lot of the struggle students have isn't with the math concept, but with the sort of clumsy, non-unified way we've traditionally presented the number system?
Could it be that the base 10 system is actually far more efficient and intuitive than we make it seem, if only we taught its inherent algebraic structure from the start?
Yeah. It suggests maybe the complexity isn't in the system, but in the fragmented way we've drawn the lines and explained the parts. This unified view seems to dissolve some of that accidental complexity.
A unified system for a complex world indeed. Definitely something to mull over.
Absolutely.
Join us next time for another deep dive.